Hello, everyone, and welcome to lecture number 3 of the 2020 Advanced Earthquake and Tsunami Hazards Training course. My name is Sean Hutchings. I'm a geophysicist with the U.S. Geological Survey Earthquake Science Center in Menlo Park, California. And I am very excited to be talking to you today about the seismicity of Indonesia, with an emphasis particularly on subduction and deep earthquakes. Here's the outline for our talk today. We'll begin first with a review of plate boundaries and earthquake distributions and faulting, followed by a brief tectonic summary of the Indonesian region, followed by an overview of Indonesian seismicity, and cross-sections and 3D profiles of Indonesian seismicity, and a brief discussion on the mechanisms of intermediate and deep earthquakes. We'll close out with a quick summary. So let's go ahead and get started with the review. So a quick review. Earth's lithosphere is divided into rigid plates, which can move independently of each other via plate tectonics. The boundaries in between these plates can either be divergent, where plates are pulling apart, convergent, where plates are moving together, and transform, where plates move laterally past each other. So divergent boundaries, tension is the primary stress and results in thinning of the lithosphere. There are two types: mid-ocean ridges. Thinning of the lithosphere causes partial melting of the mantle and eruption of new oceanic crust during seafloor spreading. And in continental settings, thinning of the lithosphere forms Rift Valley, which, if then continues long enough, may result in the formation of a new ocean basin during what is called continental rifting. The primary faulting type in divergent boundaries is normal. Transform boundaries accommodate lateral shear between plates, and the primary faulting type is strike slip. It can either be right lateral or left lateral. Convergent boundaries occur in regions of compression, and there are three primary types. We have oceanic-oceanic, where both converging plates are composed of oceanic lithosphere. Oceanic-continental, where one plate is composed of oceanic, while the other is composed of continental lithosphere. And then we have continental-continental, where both converging plates, excuse me, are composed of continental lithosphere. So in both cases of oceanic and oceanic-continental, subduction may occur if if one plate is sufficiently dense to descend beneath either younger, more buoyant oceanic crust or more buoyant continental crust. However, in the continental setting, subduction is difficult due to the buoyancy of both continental plates, and thus a suture and orogenic belt form instead. The primary faulting types in these regions are typically thrust or reverse. So with stresses being highly localized at the plate boundaries, seismicity is also highly localized at the plate boundaries worldwide, as we can see here. So the majority of which are shallow, with intermediate and deep earthquakes, so basically anything deeper than 100 kilometers, showing up in developing or well-developed subduction zones. So let's first quick review on faulting. So a fault is a fracture along which relative motion has occurred, fracture within the Earth. So for this example, the normal fault shown here, the hanging wall block, which lies above the fault plane, has moved down relative to the footwall block, which is below the fault plane. So faults occur due to brittle failure within the Earth's crust, and often behave as a stick slip. So meaning as friction on the fault plane allows elastic stress to build up, which is then released via elastic rebound in the event of an earthquake. So fault types refer to the relative motion which has occurred. So dip slip refers to vertical motion. There are three primary types. Reverse indicates hanging wall. So once again, the block that lies above the fault plane has moved up relative to the footwall, which lies below the fault plane. And reverse faults are at an angle of 45 degrees or more. A thrust fault is the same as a reverse fault with hanging wall up motion, but at a shallower angle, typically less than 45 degrees. And normal faults occur as a hanging wall, excuse me, occur as hanging wall down at an angle typically greater than equal to 45 degrees. The lower angle version of a normal fault is called a detachment, which is not shown here. So strike slip refers to lateral motion and can either be left lateral or sinistral or right lateral or dextral. And oblique slip is a combination of dip slip and strike slip mechanisms, such as the normal plus right lateral motion here, or reverse plus left lateral here. So individual earthquakes can be expressed as focal mechanisms, or beach balls, which are stereographic representations of two mathematically equivalent fault planes over which slip occurred, and also indicate the type of slip that occurred. So in the example of the strike slip fault shown here, we have two equivalent fault planes. The highlighted one is the dextral sense, and the beach ball to the right shows areas of compression shaded and areas of tension that are not shaded. So this can be applied for all the major fault types, including the dip slip. And oblique, of course, is any combination of the dip slip and strike slip mechanisms. So as a quick reminder, thrust faults are basically low angle reverse faults with a dip angle typically around 30 degrees. In a traditional crustal sense, they superimpose older rocks above younger rocks. However, the same mechanism can be applied at the plate boundary scale, where in subduction zones, for example, the shallow plate interface between the subducting plate and the overriding plate here behaves as a giant thrust fault, which is termed a megathrust. Megathrusts are known for their ability to generate the among the largest magnitude earthquakes on Earth, including those exceeding magnitude 9.0, and are thus understood to be prevalent seismic hazards to any coastal communities nearby. So also within a subduction zone, there is a very narrow inclined seismic zone of intermediate to deep earthquakes that traces this, the geometry of the slab as it subducts into the mantle. This inclined seismic zone is called the Wadati-Benioff zone and reflects intraslab deformation, which is and where intraslab deformation is the primary source of intermediate and deep earthquakes. So if, once again, here's our subduction zone. So if conditions remain preferential, meaning typically the slab as it subducts remains relatively colder and more brittle compared to the surrounding mantle, the Wadati-Benioff zone can trace earthquakes to the boundary between the mantle transition zone and the lower mantle. Below the transition zone, temperature and pressure conditions are typically too great for brittle failure, and thus ductile deformation is preferential. So the important thing to remember is that since the Wadati-Benioff zone traces the geometry of subducting slabs, this will be very useful throughout the rest of this presentation as we investigate Indonesian seismicity. All right, so tectonic setting of Indonesia is very complex, and it lies at the intersection of the triple point conversion between triple point convergence between the Indo-Australian plate here in the south, the Sunda plate, which is part of the broader Eurasian plate, and the Pacific Plate, which broadly includes the Philippine Sea and Caroline Plates. So in the south, the Indo-Australian Plate converges northward with the Sunda and Pacific Plates, typically between rates of about 50 to 80 millimeters per year, and subducts within the prominent Sunda-Java Trench. Convergence is more complexly partitioned amongst several microplates in the east, being the Timor Plate, the Banda Sea Plate, the Molucca Sea Plate, and the Bird's Head Plate. Interactions among these microplates is complex and involves subduction, such as that in the Sulawesi Trench, and collision, such as between the Banda Arc and Australia here in the south and the Timor Trough, and within the Molucca Sea collision zone here. In the northeast, convergence is primarily between the Sunda Plate and the Philippine Sea Plate, where the Philippine Sea Plate subducts beneath the Sunda Plate around 100 millimeters per year. So this complex tectonic setting also makes Indonesia one of the most seismically active regions in the world, such as shown here, with the majority of seismicity concentrated at or near the plate boundaries. So focal mechanisms shown here for events of magnitude 6.0 and up for a 20-year period show the complexity in how the tectonic motions are accommodated throughout the region. Focal mechanisms and their relation to the tectonic motions will be very useful as we in a later lecture. For this lecture, we will be focusing primarily on plotting hypercentral locations obtained from the US Geological Survey Earthquake Catalog, typically for over a 20-year period, past 20 years, for events exceeding greater than or equal to magnitude 4.0. We will do this to visualize the spatial distribution of seismicity in Indonesia, and also use these to plot cross sections to visualize subduction. Focal mechanisms, where plotted, are from the Global Centroid Mechanism Tensor project. So the GCMT project, Global Centroid Moment Tensor project, and any individual examples are from the US Geological Survey's Earthquake Catalog. Any plate boundaries shown are from the updated digital model of plate boundaries by Peter Bird, 2003. And slab geometry models, which are useful for cross sections, are obtained from slab 2.0 from the US Geological Survey by Hayes 2018. All right, so let's begin diving into Indonesian seismicity. So as previously mentioned, Indonesia is one of the most seismically active regions on Earth. Shown here are approximately 5,300 events of magnitude 4.5 and above over a 5-year period, so over the past 5 years, which is pretty incredible how frequent seismicity is. And since we know from our review that seismicity is typically concentrated within the plate boundaries, doesn't take too much imagination to visualize where the major plate boundaries are, and even without them being plotted. So the majority of these events are smaller in magnitude, clearly. However, there are several that have exceeded magnitude 7.0. And some of these did cause damage, such as the magnitude 7.5 in Palu in 2018. So if we expand this to 20 years, of course, a similar trend is seen. And this is for events of magnitude 5.0 and above over 20 years. So what we can also see is that the frequency of larger magnitude events has also increased, with several in the past 20 years exceeding magnitude 8, with the largest being the magnitude 9.1 Great Sumatran earthquake in December of 2004. So not only is the region incredibly seismically active, but the potential for large magnitude earthquakes is not uncommon. In fact, Indonesia holds 25% of the world's largest recorded events since the year 1900, 4 of which have occurred, these 4 have occurred within the past 20 years, the majority of which occurred via megathrust events, which we talked about briefly in the introduction, with one being the largest strike slip event ever recorded, and the other being the largest intraplate or intraslab event ever recorded. So this capacity for large magnitude earthquakes, and often frequent larger magnitude earthquakes, especially over the last 20 years, definitely creates high seismic risk for the region. However, magnitude is not the only factor that contributes to seismic risk. The other is the depth. So how is depth? So how are earthquakes distributed with depth throughout the region? So shown here, we have earthquakes per year for magnitudes 4.0 and above, averaged over a 20-year period, plotted against depth in kilometers. So the black curve shown here is for the Indonesian region as a whole, and each of these colored curves, shown by the legend up here, are for individual subregions, which we'll explore later. So at first glance, what we can see is that the vast majority of the earthquakes that occur on a yearly basis are shallow, typically less than 50 kilometers. So shallow earthquakes definitely pose a greater seismic risk because of their closer hypercentral distances to the surface, and also combined with the potential for large magnitude earthquakes further compounds the seismic risk. So this concept and associated seismic risk will be explored in a later lecture. So for this lecture, what we're mainly concerned with is how are earthquakes distributed at intermediate and deep, deeper depths. So overall, we can see that from about 50 kilometers depth, there's a gradual decrease in seismicity, followed by a peak in seismicity at the upper boundary of the low mantle transition zone around 410 kilometers, or MTZ. And seismicity increases within the mantle transition zone and decreases abruptly upon exiting at around 660 kilometers. So this increase in seismicity is often attributed to viscous resistance of the mantle, since there are prominent phase transitions that happen at the upper and lower boundaries of the mantle transition zone, and thus the mantle is more resistant to subducting slab moving through. But what we can also see here is that intermediate and deep earthquakes are not evenly distributed throughout the region. So for example, this green curve here, which represents northwestern Sumatra, deep earthquakes are no longer occur deeper than about 220, 230 kilometers. And then here in the red curve, which represents Java, or the southern southeastern Sumatra and Java, there's a seismic gap between about 350 and 510 kilometers. And a similar decrease in the Celebes Sea, which is this purple curve here. So we'll investigate these observations later. But the important thing to remember as well is that as these intermediate and deep earthquakes trace the geometry of subducting slabs, we should be able to see these in cross-section. So first, how are these intermediate and deep earthquakes distributed spatially? So from our graph, we kind of got a bit of an idea, but subduction is clearly concentrated within the Sunda-Java Trench near this Timor Trough in the Banda Sea region, where there's a complex geometry, and also in the Celebes Sea region between Sulawesi and the southern Philippines. So at first glance, well-developed, frequent deep earthquakes are present in the Celebes Sea, and also in the Banda Sea, but start become increasingly less frequent until practically non-existent farther to the northwest in Sumatra, which is what we had observed in our earthquake versus depth plot. So in order to get an idea of excuse me, the geometry of these subducting slabs, we can plot cross sections. So we'll go through each one of these cross sections one by one. We'll typically split it up by region, introduce each region, and then we'll go from there. So let's first start in the Celebes Sea region with cross sections A prime and B prime. So the Celebes Sea region is located between northeastern Indonesia and the southern Philippine island of Mindanao. And this is all events of all depths shown here. And it is an incredibly seismically dense, the activity is incredibly dense in this region, primarily concentrated in this narrow band between the north arm of Sulawesi and Halmahera, and also within the Philippine Trench here. So deeper earthquakes are noticed dipping off to the west here, getting progressively deeper as we move to the west beneath the Celebes Sea, and extend from Sulawesi up into north of Mindanao. And intermediate earthquakes are noticed inboard of the Philippine Trench, and also in a cluster kind of to the northeast and below Halmahera here. So the region here is very tectonically complex. It's currently a site of active volcanic arc collision, and the only active case of double subduction known on Earth today. So the Molucca Sea Plate has completely subducted both to the west beneath the Songi volcanic arc, and to the east beneath the Halmahera volcanic arc here. And between them shows no surface expression and is buried beneath the growing collisional complex in this region called the Central Ridge. So farther to the north, this collision is not nearly as pronounced. And if we start viewing in cross-section, we can get a good idea of what this looks like geometrically. So if we start with A prime through the island of Mindanao, you can see clearly the Songi slab, which is the western portion of the Molucca Sea Plate, dipping fairly steeply off to the west here, and is seismically active to near the lower boundary of the mantle transition zone. And in fact, is actually quite seismically active within the mantle transition zone. And then within this zone of very dense seismicity, without geometrical help, it would be difficult to see where the Philippine slab actually is. But in this region, it's only seismically active to about 200 kilometers, according to the geometry. However, these hypocenters over here might be related. It's unclear. And then also in the west, there is a east dipping slab called the Cotabato slab, which is only active to about 100 kilometers. So both the Cotabato slab and Philippine Sea subduction are younger than the Songi slab, just based off of the length. And if we move farther south, since collision isn't exactly obvious, like the geometry of the collision isn't exactly obvious this far north, if we move farther south to cross-section B prime, we get a very different picture with the characteristic U-shaped seismic zone and geometry of the subducted Molucca Sea Plate beneath the Halmahera and the Songi arcs. So once again, the Songi slab dipping off to the west to near the lower boundary of the mantle transition zone, and the Halmahera slab, which is only seismically active to about 320, 330 kilometers, is dipping more steeply off to the east. So, and in between them, this region of very dense seismicity is the growing collisional complex. between the colliding volcanic arcs, which form the Molucca Sea collision zone. So clearly the greater length of the Songi slab is indicative of its greater age compared to the Halmahera slab. So subduction of the Songi slab began approximately 20 million years ago, whereas subduction of the Halmahera slab began approximately 10 million years ago, following the collision of the Australian continental margin with the Sunda Shelf. And it's also very clear that it's a very seismically active region. So if we view this in 3D, we can get a better idea of the geometry here. So the top panel here is plotted seismicity, everything deeper than about 50 kilometers, just so we could more clearly see the deeper seismicity. And the bottom panel is the accepted geometrical model from Slab 2.0. And so if we start here, viewing from the north, we start moving around to the east here, you can see the Halmahera slab present, and the U-shape of the Molucca Sea plate actually follows geometry very well. So the Halmahera slab is not nearly as extensive as the Songi slab. Songi slab is active from basically Sulawesi up into the southern Philippines, whereas the Halmahera slab, which is slightly obscured by seismicity within the Philippine Trench, is only active to not much farther north than the island of Halmahera. So if we come around again, you can see there's this hard kind of 90-degree bend in seismicity here around Sulawesi. So this is related to subduction within the northern Sulawesi Trench, which we will investigate next. So Sulawesi, located just kind of to the southwest of the Molucca Sea collision zone, is not nearly as seismically active, with the majority of seismicity being concentrated in the kind of the central northern portions of the island. So subduction is, as mentioned earlier, is active within the northern Sulawesi Trench, and is above the Songi slab, which the deep hypocenters up here in the corner we can see are from the Songi slab. And if we move south from the trench, you can see a clear transition from shallow to more intermediate and deeper earthquakes here. So if we view this in cross section along CC prime, you can clearly see the southward subduction of the Celebes slab, seismically active to between 200 and 300 kilometers here, and it follows the accepted geometry quite well. And also to the south is a more diffuse feature called the Sula slab, for which no geometrical models were available, so this is inferred, but it is dipping very steeply to the north. So what's going on here? So the Sula slab, based off of, so there's no, like the Celebes slab, there's no surface expression, so there's no active trench in the Gorontalo Bay area, which is just south of the north arm of Sulawesi. And tomography evidence as well as geologic evidence on the surface indicates that the Sula slab is a remnant of older subduction that predates subduction of the Songi slab, so earlier than about 20 million years. So tomography indicates that the lower half, like the lower portion of the Sula slab, has broken off and descended aseismically into the mantle, and leaving just this what's left of about 200 kilometers attached to the former subduction margin. So following the season subduction, the Songi slab began subducting. The deeper hypocenters down here, which are part of. So subduction within the Celebes slab is rather young, starting about 5 million years ago, and its interaction with the Sula slab has deformed it more into its steeper orientation visible here. So the Celebes slab is very active, has produced damaging megathrust events in the past, such as the 1990, the April 1990 magnitude 7.6 event. So if we move farther to the east into West Papua, so subduction in this area is primarily accommodated within the New Guinea Trench, which runs basically from the Philippine Trench across the length of Papua New Guinea, and accommodates approximately 70 millimeters per year of direct convergence between the Australian plate to the south and the Pacific plate to the north. So subduction geometry is rather complex. It's a fairly flat slab determined from seismic tomography, having a very shallow dip in between about 10 and 30 degrees. And as we can see here from hypocenters, does not appear to be seismically active below about 200 to 300 kilometers. So in the west, geometry is very complex and not entirely understood. So this region here is actually site of very oblique convergence, and strike slip motion is the primary motion that exists in this area. So there's not much direct convergence. And also, if we move farther to the southwest, there's another denoted as a subduction zone by plate boundaries called the Tsunami Trench, which is kind of this curved area here, which is related to the collision between the Bird's Head microplate and the Banda Sea microplate here. So if we view these two subduction zones here in cross section along D prime, this is what we get. So you can see in the New Guinea Trench, at the Bird's Head, the subduction is not very well defined, and is kind of vaguely seen dipping to the south, only active to about 100 kilometers. So it's not, there's no existing geometrical models for this region, for this area. So it's unclear whether this is a relatively young addition to subduction within the New Guinea Trench, or this is a result of the increasingly oblique convergence. So there's not a very strong convergent component here, and thus not subducting as deep. So if we move to southwest here, in the Tsunami Trench, there is a noticeable Wadati-Benioff zone here, active to about 200 kilometers. Excuse me. So recent research has actually indicated that this is the Tsunami Trench is actually no longer a site of active subduction or very dormant subduction, and is more closely related to the curved collisional complex between the Australian and the Sunda plates, which we'll investigate here in a moment. So this, so the Tsunami Trench is often termed a trough in this case, as it's likely no longer an active marine trench. So this Wadati-Benioff zone here, due to tomographic evidence, has been suggested to be part of the curved Banda slab, which we will investigate next. And it is only active to 200 kilometers here due to a slab tear. So if we move farther southwest into the Banda Sea, which is probably the most complex tectonically and seismically region in Indonesia, as you can see here from the very unusual plate boundaries. So the Banda Sea is a complex region of convergence and subduction, and or at least former subduction and an extension as well. So approximately 15 million years ago, a kind of curved embayment of Jurassic Age on the northern margin of the Australian continental plate, continental margin, arrived at the subduction zone and caused intense slab rollback that contributed to this curved shape. And approximately 10 million years ago, the Australian continental margin began colliding with the outer Banda arc. So subduction is likely no longer active in the Timor Trough area and extending all the way into the Seram area, where this is all primarily collisional. So if we view this in cross-section along cross-section line E to E prime, we can see a very unusual shape with a poorly defined Wadati-Benioff zone at the shallower depths with much more dense seismicity towards approaching 600 kilometers, and kind of a reversal and dip here, which kind of loosely follows the accepted geometry. So what we can see here is essentially a synformal lithospheric fold that has developed. And this is due to the collision of so this is due to slab rollback, for one, into the Jurassic embayment, fairly fast convergent rates, as well as lithospheric delamination. And following the collision of the Australian continental margin with the Banda arc, the mantle is increasingly more resistant to tectonic motion, and thus continuing to fold the slab, which you can get a better idea of its complexity in 3D. So once again, starting here, looking from the north, if we move around to the east, you can see the complex, it's kind of a west dipping synform that has been formed here, which has often been likened to like the bow of a ship, or like a bathtub, or a spoon shape almost. Regardless, it is very complex, and seismicity actually traces very well along kind of the axis of the synform, all the way down to deeper than 600 kilometers, and with some seismic gaps kind of on the southern limb and the northern limb here. But regardless, the seismicity actually traces the slab very well compared to the models. And when we begin moving farther to the west, subduction geometry simplifies greatly. So moving to the west, here we have southeastern Sumatra and Java. So here, some subduction is fairly easy to visualize now. It's mainly just one slab of Australian oceanic lithosphere subducting beneath the Sunda plate. But what is interesting here is that the amount of, kind of how we were observing earlier, both in our earthquake distributions plot and in the graph, the amount of deeper and intermediate earthquakes starts to decrease rather rapidly, actually, moving farther to the west into Sumatra. So if we view this in cross-section, so starting through with cross-section FF prime through Bali, looking into eastern Java, what we can see is a very well-developed Wadati-Benioff zone to about 200 kilometers. And then there's a very large seismic gap of about 300 kilometers missing, where seismicity picks up again at around 500 kilometers. So geometrical models show that the slab is still present here, or is likely still present here. So what exactly is going on at this location? So at this region in eastern Java, seismic tomography has proposed that slab tear and a large hole within the slab is the reason for this seismic gap, rather than it being just an aseismic section. So if we move to cross-section G prime, which is in southeastern Sumatra, once again we see kind of a similar trend where it's, although the Wadati-Benioff zone is a little more poorly defined to just over 200 kilometers, but then the seismic gap is quite a bit bigger here, with a single event below 600 kilometers and geometry indicating that the slab does still extend to within the mantle transition zone. So there's no tomographic evidence that suggests a hole or a tear in the slab at this point. So this may just be an aseismic section where the properties of both the ambient mantle and the slab are not conducive to seismicity. But also in this location, as we start moving into Sumatra, convergence between the Indo-Australian plate and the Sunda plate becomes increasingly more oblique, which we will begin to see more later. So if we view this section in 3D, you can see again. So once again, the geometry is of the subduction is fairly simple. It's just striking how many aseismic sections are present. So the whole seismic hole is beneath East Java, has tomography evidence to back it up, whereas over here it's not nearly as clear. So if we keep moving into to the northwest into Sumatra, continue to see this trend, how basically above about 3 degrees south, deeper earthquakes basically become non-existent, and intermediate earthquakes become less frequent. So in this area, once again, the Indo-Australian plate is converging kind of to the north-northeast with the Sunda plate. So the farther we move to the northwest along the subduction zone, the more oblique the motion becomes, with a considerable dextral strike slip component being accommodated by the Great Sumatran Fault, which runs the approximate length of Sumatra, not shown here. So if we begin through kind of southern Sumatra with cross-section H prime, we can see kind of a similar trend that we saw in the previous cross-section. However, there is no deep seismicity at all, even though geometrical models indicate that the slab does continue. The Wadati-Benioff zone is fairly well defined to about 250, not so well defined to about 300 kilometers. And the slab dip is also fairly steep here. So if we move northward to about just under 1 degree north, the orientation changes rather abruptly. So the slab dip, for one, is much shallower, and is only seismically active to about 250 kilometers. And geometrical models do have trouble tracing this slab beyond this point as well. So once again, at this area, there's increasingly oblique motion, which may result in less of a convergent component, and therefore the slab might not penetrate as deeply. And also, just north of this location, a slab tear, a prominent slab tear, has been proposed to exist, likely due to this increasingly oblique motion, which, as we move to the north of this, once again, orientation has changed again, seismically active to a little bit deeper, and the geometry indicates a steeper dip. So this is to the north of the proposed fold, which the research that proposed this indicate that slab dip is relatively shallow, just south of the fold, and then becomes steeper again, just to the north of the fold, which is kind of what we see here. So though the slab is not as traceable beyond about intermediate depth. This section of the subduction zone is quite active and was responsible for the Great Sumatran earthquake in 2004, the Great magnitude 9.1. So the mechanisms, intermediate to deep seismicity can occur by a variety of mechanisms. Primarily, and it depends on the properties of both the surrounding mantle and of the subducting slab. So, such as temperature, strain rates, the rheology, any inherited weakness, such as any older fault zones or fractures in the slab, and the mechanisms by which these events can occur, which are similar to their shallower counterparts, it's just they occur at far greater temperatures and pressures than the surface. Can include anything from slab flexure to metamorphic dehydration as the slab descends, and thermal shear runaway as another mechanism. So, very very complex. And if we here's a couple of prominent examples of large deep earthquakes. So these, I mean, despite their differences, they still have the capacity to reach great magnitudes. So a couple of examples, as they also vary greatly in their focal mechanisms, such as the 2004 magnitude 7.3 that occurred beneath southern Sumatra at 582 kilometers depth at due to oblique normal faulting. So oblique normal faulting is a common form of intraslab deformation, usually attributed to slab flexure as the slab bends and as it descends into the mantle, and also metamorphic dehydration can cause contraction and therefore tension. So slab flexure can also create intralimb shear, which can create reverse fault mechanisms or thrust mechanisms parallel to the dip, which may be the case with the 2007 magnitude 7.5 beneath Java. Slab unbending also can create reverse or bending in the opposite direction as it descends may also create reverse mechanisms. And an interesting one would be the magnitude 7.0 in 2015 beneath the Banda Sea. As we know, the Banda Sea is undergoing some very complex and intense deformation. So this strike slip mechanism may be related to that lithospheric folding, and also maybe some inherited fracture zones that were present within the slab prior to subduction. So those are just a few examples of the complex mechanisms that could be exhibited by intermediate and deep earthquakes. All right, so we've reached the end here. So just a quick summary. So Indonesia is a very complex region of very high seismicity and thus high seismic risk. Seismicity is heavily concentrated within the plate boundaries, which we'd expect. The depth distributions of intermediate to deep earthquakes trace the Wadati Benioff zones, subducting slabs, and exhibit geometry that is comparable to accepted models, which is great. And then deep intraslab events differ in how they in their source mechanisms and also in their the type of focal mechanisms that they exhibit than shallow earthquakes. And also intermediate deep earthquakes, while very interesting, are not associated with high seismic risk. So in part 2 of this lecture on continuing on in our investigation of Indonesian seismicity, we will investigate shallow and crustal events and their associated risk to communities on the surface. That's all. Thank you for your attention, and here are the references. And hope you have the great rest of your day.